Hello, everyone. This is the lesson for rational functions. It's talking about analyzing graphs of them. We have looked at some graphs just by using them to solve equations and match up equivalent functions, but now we're going to talk about why they look like the way they do. So first, we're going to start with our parent function. That parent function is y equals 1 divided by x. Any rational function has a variable in the denominator. That's what makes it a rational function. It's a fraction, it's a ratio. So that function is going to look something like this. You're going to graph it. Let me pull up my Desmos here. And it looks like it's got kind of two separate parts, a curve going up here and down there. And it's never going to hit the x-axis or the y-axis. So you can see how it kind of, as it goes closer and closer to zero, that just continues to go up and up. And the same thing goes as it goes closer and closer to zero from the left side. It goes down and down and down and down and down. Same thing for the right side. It'll never cross the x-axis on the right, nor will it do it on the left. So those have special names, those vertical and horizontal lines. You can all divide by numbers, so I'm not going to focus on those numbers, but what you want to be able to do is kind of eyeball what a graph looks like and sketch it on a piece of paper. So it's going to look something like this. And let's fill in some of these answers. So what happens to y as x approaches 0 from the left side of the graph? So the left side of the graph being over here, as it gets closer and closer to 0, y sharply turns downwards. So it actually approaches negative infinity. Goes down. And the same thing on the right side of the graph. As it approaches 0 from the right side, it sharply turns up. So it approaches infinity. Will the graph ever touch a point at x equals 0? No. Will it ever touch a point at y equals 0? Also no. There is no point here. The point 0, 0 doesn't even exist. So those points are called discontinuity. So since it can't touch at x equals 0, we call it a point of discontinuity, which represents a break in the graph. So it's continuous if you can draw the graph without lifting your pencil up. It's not continuous if you have to lift your pencil to cross over and draw another part of the graph. Also, looking at your graph, if you go to Desmos and you have it graphed in here, if you go to your table settings, it'll say undefined at 0. Well, you can't divide by 0. 1 divided by 0 is not a number. So that's why the graph will say undefined. Or on your TI calculator, it'll say error. So that's another way to look at it too. So since the graph rises sharply up and down on both sides of x equals 0, we call that line x equals 0, that's vertical. It's called a vertical asymptote. Spelled A-S-Y-M-P-T-O-T-E. It means a graph, a straight line that the graph will never touch, but it approaches. Similarly, we can do y equals 0. That's going to be a horizontal asymptote. And let me show you what those look like on the graph. So you can see the graph of 1 over x. If I type in x equals 0, it's going to throw a vertical line right where the y-axis is. Can you see that? That's the vertical asymptote. Of course, if we change that 0 is the only spot where the graph doesn't touch. So we're going to leave that at x equals 0. Similarly, we can do y equals 0. And that's going to be the horizontal asymptote. And if I move over there, I can move that up and down too. But again, right here, it's centered right at 0. So y equals 0 is going to be your horizontal one on this graph. So we say the domain of the function is all real numbers except for 0. And the range is also going to be the same. Graph this in Desmos. Let's take a look at it and see if we can pick apart this function and figure out what needs to be answered here. So we got to see how this graph moved from the parent function 1 divided by x. So what I'll do is I'll put that in the graph. The graph is y equals 1 divided by x minus 3 plus 2. Let me get rid of these asymptotes, but I'm going to leave 1 divided by x in there. So if I do y equals 1 divided by x minus 3 plus 2, and hide that for a minute. Let's take a look, see if we can zoom out a little bit. Looks like the graph moved in this direction. And how many did it move? We can actually get those numbers from the equation itself. So the 3 and the 2 are the directions that indicated it moved. Since it went x minus 3, that's in dealing with the x, that's right or left. It happened to go right 3, and it went up 2. So you can see right 3 and up 2 from there. And if I kind of piggyback that, if I make my vertical asymptote x equals 3, and my horizontal asymptote be y equals 2, and let me hide this first one here. You can see that graph is centered around the imaginary coordinate 3, 2. Okay, it will never touch 3 for the x value, and it'll never touch 2 for the y value. So the graph moved right 3. That comes from here. Notice it's the opposite of the sign. And it went up 2. What's the point of discontinuity from the graph? Well, it's going to be x equals 3 now. And on your table, if you plug 3 in, it'll say undefined because we can't divide by 0. And if I plug in 3 here, I'm going to get 3 minus 3, which is 0. So that's going to be an undefined number there. See, all the other numbers work. But 3 does not work. So our point of discontinuity is x equals 3. That means the vertical asymptote is also x equals 3. The horizontal asymptote will be y equals 2. So it's going to come right from these numbers. The domain, all real numbers, except 3. And the range, the y values, all real numbers, except 2. Now we want to graph that. So on the back side, let's sketch a graph of this. The asymptotes are what you want to draw first. So the vertical and the horizontal asymptotes, since they got shifted, the vertical asymptote is going to be at x equals 3. I like to do a dashed line for the asymptotes. So I'm going to put a dashed line at x equals 3, and that's my vertical asymptote. And then my horizontal asymptote, y equals 2, well, that's going to be right here. HA stands for horizontal asymptote. And then from there, I want to fill in the rest of my graph. So since it's the same look of my other graph, I'm just going to fill in a rough sketch of it, making sure we don't cross over those asymptotes. And that would be a good, a rough sketch of what that graph looks like. See if you can do this one on your own. So you pause the video and attempt it yourself, and we'll check it in a little bit. All right, have you made an attempt to try it on your own? If not, pause it, graph it in Desmos if it helps, and see if you can answer the questions down here and sketch a graph. All right, hopefully you've had a chance to check it. The question says, how did the graph move from its parent function of 1 divided by x? Well, in the previous problem, it was -3, and it went to the right. So if it's plus, that's going to be to the left. So it should go left 4. And this -5 at the end is going to indicate it goes down, so down 5. The point of discontinuity is going to be x equals whatever makes this 0. So since the restriction is -4, that's going to be -4. That means your vertical asymptote is going to also be x equals -4. And your horizontal asymptote is going to be y equals -5 since it went down 5. So the domain is going to be all real numbers. Except -4. And the range is going to be all real numbers. Except -5. So to graph that, you're going to similarly do what you did for the number 2 graph. You're going to do your vertical and horizontal asymptote. So I'm going to go to -4. There's your vertical asymptote, x equals -4. And your horizontal asymptote is going to be y equals -5. That's going to be right here. And it's going to be centered right around that. So we would make sure we don't cross over the axes. And there should be a graph. Graph it in Desmos. I'm not going to put that on here just for time purposes on the video, but graph it in Desmos to double check that you have that. Remember, Desmos won't graph the asymptotes, but you can type in x equals -4 and y equals -5 if you want to see them on there. All right, let's read number 4. The question says, write a function that is shifted 5 units to the right and 1 unit down from the parent function. Looks like I spelled parent wrong. Y equals 1 divided by x. Check in your y equals, Desmos. So let's look at the requirements for how it moved. 5 units to the right. So that means in the denominator, it's going to be x. And remember, right is the, it's the opposite. So you think on the x-axis, it goes in the right direction. That's positive, but it's really going to be minus. So x minus 5 is going to be 5 units to the right. Let's verify that on Desmos too. Okay, I got a little ahead. I had to pause the video and I forgot that I'd paused it and I started teaching it. But basically on this problem, if you make the x minus 5 on the denominator, it's going to shift it to the right. And if you make it -1, after the fraction, it's going to shift it down. So it's going to go right 5 and down 1 from the parent graph of 1 divided by x. So that means the new point of discontinuity is going to be whatever makes this 0, and 5 minus 5 is 0. So your restriction's 5, the point of discontinuity is 5, your new vertical asymptote is going to be x equals 5. The horizontal asymptote is going to be the amount it shifted down, so y equals -1. And that'll change the range to all real numbers. except 5, the domain, not the range. And the range will be all real numbers except -1. Remember, domain is x values and range is y values. All right, so we want to, our last example, we want to see how these can graph when they're not just 1 divided by something. We're going to have different numerators other than 1, and that's going to change how the graph looks and some of the features. Sometimes you're going to have more than one asymptote. For instance, if I have a graph 1 divided by x squared, let's say -9, you're going to notice that it has 2 asymptotes, one at -3 and one at +3. And that's because -3 and +3 both square to 9. 9 minus 9 is 0, so those are both points of discontinuity. On this problem here, notice that there's an x squared on the denominator. In fact, if I just did x squared minus 2x minus 15, you can see that it gives me zeros at -3 and +5. And those are both numbers that I'm not allowed to divide by, because if I plugged in -3 or +5 in the denominator, it's going to give me 0. Can't divide by 0. But if you look at the graph, it's going to appear that it only has one point of discontinuity. And that looks like that's going to be at the 5. So what we want to do here is look at your table for a minute. And we might have to adjust some of the numbers that we're putting in. I'm going to go up. And I'll start at -5. Sometimes you have to go higher in the negatives, and sometimes you have to go down further. But you'll see at -3, it gives me an undefined point right there. Notice that one of the points is kind of basically hopped over. So at -2, it gives me a value. At -4, it gives me a value, but it doesn't give me a value at -3. If I continue downward after 2, it'll also give me another undefined at 5. But that at 5 is where the asymptote is. If you actually typed in x equals 5, it'll give you a vertical line at the asymptote. It will not give you a vertical line at -3. But the restrictions are going to be from your table, -3 and +5. -3 and +5 both give you undefined. So those are your restrictions. So let's note that on the paper. Those are also going to be the points of discontinuity, which, again, points of discontinuity are the same as restrictions. So you can interchange those. Restrictions we tend to use for numbers when it's not in a graph. Discontinuity are points we tend to use when we're drawing the graph and we lift our pencil up. So your domain is all real numbers except -3 and 5. Not just 5, but -3 as well, even though it doesn't have a vertical line there. Only one of those is going to be the vertical asymptote, and that's going to be x equals 5. Now let's go back behind the math and understand why that is. So what happens is, on this problem, x squared minus 2x minus 15 can be factored into two binomials. And you can do that by looking at the last number, -15, and finding two numbers that multiply to negative 15 that'll also add to negative 2. So I know 5 and 3 multiply to 15. I can get them to add to negative 2 if the 5 is negative. So my factor is going to be x minus 5 and x plus 3. So you can see that your restrictions are going to be x equals 5 and x equals negative 3. Those are values that when you plug them into the denominator, they give you 0, and you cannot divide by 0. But the reason that you're not seeing that 3 as a vertical asymptote is because if you draw, or if you simplify this, x plus 3 over my factored form, what's going to happen is the factor x plus 3 will cancel. And that's just going to leave me with my denominator being x minus 5. And when I don't have anything left over, you just put a 1 there. Because 1 times anything is whatever that number is. So if I cancel those out, I'm going to be left with 1. So that's actually my simplified form. The vertical asymptote is only going to be the restrictions that is left over. The one that I removed when I simplified was which point of discontinuity did you remove when you simplified? That's going to be this negative 3. The non-removable one, the one that's left over, that's going to be the positive 5. So the 5, the one that's left over, the non-removable point, is your vertical asymptote. We call the one that's removed a hole in the graph. And here's how you think of that. Again, analyze this graph for a second. You got all these points plotted. You have a vertical asymptote at 5. And you have a missing point here. That's the hole in the graph. So right there, you're going to put an open circle. So what we'll do first is our horizontal asymptote didn't change. It's y equals 0. Most of the time, it's going to be y equals 0. Our vertical is x equals 5. We're going to plot those first. Again, HA stands for horizontal asymptote and VA stands for vertical asymptote. X equals 5 is the vertical, y equals 0 is the horizontal. And if I'm going to graph this, it's going to look like these two pieces that we had in all of our graphs so far. Being careful never to cross over your asymptotes. The big difference here is we want to show that hole in the graph at x equals 3, negative 3. So the hole in the graph, if you count to the left 3, 1, 2, 3, you're going to put an open circle right there, and that's going to be your hole in the graph. So hole in the graphs are always going to be open circle. If you use pen like I did, you can just kind of draw it over it. And that's going to be at x equals negative 3. Your hole in the graph and your vertical asymptote represent all the restrictions, all the points of discontinuity. All right, hopefully that helps you guys work on the day 4 assignment. And if you have any questions, please reach out to me and let me know how I can help. Thanks a lot.